Hi, St. Peter's Engineering College, Department of VCE. Myself, Dr. Lakshmi Devi, Professor, Department of VCE, St. Peter's Engineering College. Now I'm going to cover first unit, second part, image transforms. Under image transforms, first we would like to see what are the main contents observed in this particular image transforms. Two-dimensional affective properties, Walsh transform, Hadamard transform, discrete cosine transform, discrete wavelet transform. To the maximum extent, in this particular session, we would like to complete after giving proper introduction of image transforms. Then two properties or three properties will finish off it. In the next videos, as a sequence of videos, we'll finish off the remaining properties of transforms as well as Walsh, Hadamard, discrete and wavelet transforms. Now let us see first in the image transforms, what's the importance of what's actually the transform? From where we'll get this word image transforms, and what's the importance of these transforms in the digital image processing? First, as a mathematical students, we come across Fourier series expansion of continuous function into a weighted sum of sines and cosines, or weighted sum of complex exponentials. In this, as a mathematics students, we come across already the Fourier series. From the Fourier series, trigonometric Fourier series expansion of continuous function into weighted sum of sines and cosines entered after this particular Fourier series of trigonometric, then Fourier transforms. Fourier transforms maps one function to another, continuous to continuous, mapping and integral transform. So in this, after Fourier transforms, we have discrete Fourier transforms. Discrete Fourier transform approximation to Fourier integral maps discrete vector to another discrete vector that can be viewed as a matrix operator. So in this particular concept of Fourier transforms, after discrete Fourier transforms, we have fast Fourier transforms. Fast Fourier transforms, special computation algorithm for discrete Fourier transforms. In this, after discrete Fourier transform, fast Fourier transforms are using signals and systems as well as digital signal processing as well as digital image processing. So first let us see in what way we are actually denoting this Fourier series. X of t is equals to a0 by 2 plus sigma k is equals to 1 to infinity ak cos kw naught t plus bk sin kw naught t. So where ak is equals to 2 by t naught integral of t naught x of t cos k omega naught t dt, and similarly bk is equals to 2 by t naught integral of integral t naught x of t sin k w naught t dt, where here it's omega naught, we'll call it as omega naught is equals to 2 pi by f naught, which is equals to 2 pi by t naught, which is equals to 2 pi f naught. If x of t is even in the sense x of minus t is equals to x of t, like a quotient function, then bk term becomes 0. If x of t is odd, x of minus t is equals to minus x of t, like a sine function, then ak is equals to 0. Okay. So of this particular Fourier series, we have a complex mathematics review here. That is, x square we can denote in the complex mathematics like x square is equals to minus 1, where x is equals to square root of minus 1. That's equals to plus or minus j or plus or minus I we can denote. In what we can represent this as on complex plane means on x and y coordinates, x and y axis, This z is equals to x plus jy. This is a complex plane notation of real and imaginary axis. Z is equals to x plus jy. This is the notation. So in that, what's the magnitude and phase? Magnitude r is equals to a mod of z, that's equals to square root of x square plus y square, where x is equals to r into cos theta, y is equals to r sin theta. Then phase is equals to tan inverse or arc tan of y by x, that is imaginary plane by real plane. So absolute value of z is equals to mod of z is equals to, that is nothing but magnitude square root of x square plus y square. Like this all the things in the interlevel we have already come across. The basic operations in this particular mathematics which are used in the transforms: addition, subtraction, multiplication and division only. So with this e power j theta is equals to, actually here we can observe e power j theta is equals to cos theta plus j sin theta. In this notation we can have some other equations here which are more frequently used in mathematics. So as an engineering students, without math they are subject to the maximum extent. So that's the reason this basic knowledge I am giving for understanding of this transforms and its properties in this particular session. So discrete Fourier transform for one dimensional, how you are representing means x of k is equals to discrete Fourier transform of x of n, that's equals to sigma n is equals to 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where this k is varying from 0 to n minus 1. So discrete Fourier transform after one dimensional, but here we are using two dimensional image for the transform purpose, for the processing purpose. Instead of one dimensional, we'll go for the two dimensional discrete Fourier transforms. Before going to the Fourier transforms, actually, first image transforms importance we can discuss here. Then we'll go for the discrete Fourier transforms as well as other transforms which are useful for image processing. Transform is basically a mathematical tool which allows us to move from one domain to another domain. So image transforms are useful for fast computation of convolution and correlation purposes. Transforms are not changing the information content present in the signal, rather it changes the representation of the signal by projecting it into a set of basis functions. This is the basic reason for entering into the image transforms in the image processing subject. So discrete Fourier transform is the discrete general version, is a slow in general. So fast Fourier transform is a super accelerated version of the discrete Fourier transform algorithm, but it produces the same result. The discrete cosine transform convolutes the signal with a cosine wave only, while the discrete Fourier transform and fast Fourier transform convolutes the complete complex wave, that is e power jx is equals to, or ix is equals to cos x plus I sin x. So discrete Fourier transform is a linear transform which takes input as a complex signal x of length n and gives as output a complex signal x of length n, where x is equals to wx. W is a complex n by n matrix with entities w to the power of kn is equals to exponential of minus j to pi kn by n, where kn ranges from 0. So image transforms, next one after this discrete Fourier transform and fast Fourier transforms, we have discrete cosine transform, which is a linear transform and it takes input as a real signal x of length n and gives as output a real signal x of length same n. It is computed by taking d of t of the signal y of length 2n, which is the concatenation of the signal with its reverse, that is y is equals to x of 0 to x of n minus 1, and the same way x of n minus 1 to x of 0. That is, since y is a symmetric, its DFT is real. In order to show the symmetric, we are representing this x of 0 to x of n minus 1 and x of n minus 1 to x of 0. Then FFT, after DFT, we are observing FFT because if it's a forced computation, FFT is a collection of algorithms for fast computation of the DFT. Typically, the number of operations required by the FFT is on the order of n into log n base 2. The most famous FFT algorithms are for the case that n is a power of 2, but there are fast Fourier transforms for prime orders and for different other factorizations. In particular transforms, FFT plays a major role as compared to the DFT, but the net result of DFT and FFT are same. So periodic signals. This is the standard definition for the periodic signals. Just for recollecting purpose, I'm giving here as an introduction. A continuous time signal x of t is a periodic if x of t plus t naught is equals to x of t. The fundamental period t naught of x of t is smallest t naught satisfying the above equation. Then fundamental frequency f naught is equals to 1 by t naught, the relation between the frequency and times period. The fundamental angular frequency omega naught is equals to 2 pi f naught or 2 pi by t naught. So with this particular, now let us see the difference of sin t and sin 4t. Here just with this particular graphical representations, still if you have any ambiguity on understanding of relations between the time and as well as the frequency, it's clear for this. Harmonics in the sense integer multiples of the frequencies of the wave. Suppose if you consider this particular wave and the time period of the wave is a t naught with the 2 pi degrees, it's a t naught is the total time period of this wave. If it is sin 40 means within this particular duration, 4 times the same sinusoidal signal repeats here within 360 degrees. This is sin 40 signal. With here decreasing of frequency, that means time period here it is for 360 degrees only one signal is repeated. The t naught is very large here, but here t naught is reduces. If t naught is reduces means frequencies increases because of its relation. Then discrete time signal. In what way continuous time signal we can observe that we have already observed in the last slide, and this is discrete time signal, which is actually the discrete in nature but continuous in amplitude. That is discrete in discrete time signal. We can observe this discrete notation of the time signal. X of n is periodic if x of n plus n is equals to x of n. That fundamental period n or n naught of x of n is smallest integer n satisfying the above equation. With the smallest integer of n, x of n plus n is equals to x of n. The fundamental angular frequency ohm naught is equals to, in the discrete notations we can use the fundamental angular frequency as ohm naught, that is 2 pi by n naught. Okay, so angular frequency and ohm naught is equals to 2 pi by n naught. Then still if you want to go for image transforms and its applications, here I have given one example. Fast Fourier transform if you have applied on noisy image, this one is the noisy image of input, and fast Fourier transform if you have applied on it, the noise pattern stands out as 4 spikes in this particular transformed output. This dots indicates 4 spikes of the noise. Then by using this Fourier transformed output, we can apply the editing process. Through that editing process, we can remove these spikes of noises. Afterwards, we can apply inverse Fourier transform or inverse fast Fourier transform on this particular transformed output. Then after applying the inverse Fourier transform by removing these particular spikes of the noise, then this is the net result of output. This is the just an example of how you can remove the noise with this particular transformations by applying the first Fourier transform. How this noisy image appears to be a noiseless image. Okay, see another total process of as a first Fourier transform as a filtering in the frequency domain is of course as a convolution we'll call it as raw image. We are representing here I of mn, that is input to the pre-processing unit. After pre-processing, we can apply to the Fourier transform. The Fourier transform output we are denoting as f of uv. F of uv, if you have given, that is for filter function, where the filter function is nothing but a convolution process gets taking place. The filter transfer function, if you have denoted as h of uv, then h of uv into f of uv is an output of the filter function. Then you can apply the inverse Fourier transform over it. Then inverse Fourier transform of a multiplication of h of uv f of uv gives its output. After post processing, then the enhanced results will get that enhanced results I cap of mn or I dot of mn. Just to show the difference between the raw image to the enhanced image, we have shown like this. So with this process, you are in a position to understand exactly how the image transforms we are applying on and extracting the required things. And this Fourier transform, for continuous domain, just for continuous Fourier transforms, we are representing for one-dimensional signals. This is f of u is equals to integral of minus infinity f of x e power minus j 2 pi ux dx. Then inverse Fourier transform of this f of x is equals to integral of minus infinity to infinity f of u e power j 2 pi ux du. These are the two formulas in case of Fourier transform purpose, one dimensional. Here I have given just an example of if f of x is equals to 1 for x is less than x by 2 and 0 for x is greater than x by 2. This is actually the f of x. What is its Fourier spectrum for this f of x means, just you can apply the same formula which I have given in the last slide. F of u is equals to integral of minus infinity to infinity f of x e power minus j 2 pi ux dx. Just in place of f of x, you can substitute these values by specifying the limits minus x by 2 to x by 2 e power minus j 2 pi ux dx. Because this is 0, it's invalid, so you can consider this one only. So then 1 by j 2 pi uv, this answer once you have done the integration, and this is actually the solution for that. That will be replaced as x of sine pi ux by pi xu. That's equals to with the sinc function x into sine sinc of pi xu. So that sinc function, if you have plotted, this is the Fourier spectrum of one-dimensional signal. Here we have the Fourier spectrum as f of u. This is the way to evaluate one-dimensional signal to the Fourier spectrum of one-dimensional. Similar thing if you go actually the two-dimensional Fourier transforms. For the continuous signals, this is actually f of uv. For continuous signal, it's a two-dimensional. That's the reason double integral given. Similarly, for inverse Fourier transform, f of xy is equals to double integral f of uv into e power j 2 pi ux plus vy du dv, and this is dx dy, where uv's are spatial frequencies. Also, we'll write Fourier transform pairs as, in general, the Fourier transform pair we are denoting like this. F of xy is a Fourier transform pair of f of uv. So f of uv is a complex in general. That's why f of uv is equals to real of f of uv plus j imaginary of f of uv. So mod magnitude of this f of uv, we are representing it as mod of f of uv. And phase spectrum of this f of uv is representing as arctan or tan inverse of f imaginary of uv by f real of uv is a phase angle spectrum. Then conjugacy is a conjugate symmetry. F complex conjugate of xy is equals is a pair of f of minus u minus v with the Fourier transform pair, and just representing with the complex conjugate. This is actually the formula. Symmetry, how we are representing means symmetry on f of xy is even if f of xy is equals to f of minus x minus y. This is the symmetry property. Of course, this is the basic introduction of Fourier transforms as Fourier series, Fourier transforms, discrete Fourier transforms, then fast transforms with the one-dimensional continuous signals and one-dimensional continuous signals and one-dimensional discrete Fourier transform DFT signals given. Then first you can see the conclusion here with this particular proper introduction, and then we'll go for next uh, properties of a two-dimensional FFTs or DFTs. The FFT is a computationally efficient algorithm to compute the discrete Fourier transform and its inverse. So evaluating the sum above directly would take n square arithmetic operations. But FFT algorithm reduces that computational burden to n log n base 2 arithmetic operations. With this, the number of operations in this FFTs are reduced a lot as compared to the DFT computation. So FFT requires the number of data points to be a power of 2. Usually, zero padding is used to make this true. So FFT requires evenly spaced time series. Evenly spaced time series in case of fast Fourier transform you can use. The fast Fourier transform provides a method of speeding up the calculation of the discrete Fourier transform by reducing the number of complex multiplications and additions. So after completion of this particular introduction of Fourier transforms and its importance, and introduction of discrete Fourier transform, fast Fourier transform. As a conclusion, why we are looking into the discrete Fourier transform as well as fast Fourier transform on image processing that we discussed in general. Let us see here with the one or two slides. Use of these transforms in the digital image processing. To extract more information, transforms allow us to extract more relevant information, like how white light gets converted into, that is sunlight converted into Vibgyor colors after passing through a prism. Similarly, a transform is a tool that allows one to extract more information from a signal shown in the figure below. This is a transform. If you observe, this is a transform. Once you have given signal, it gives the spectrum. Just as an example, we already observed. If you have given time domain, it gives an actually the frequency domain as an output of this transform. So transform do not change the information content present in a signal. This introduction already I have given. Now, so use of these transforms, still if you have in digital image processing, how you are making use of these transforms, there are basically two reasons for transforming an image from one representation to another. The transform may isolate critical components of the image pattern so that they are directly accessible for analysis. The transform may place the image data in a more compact form so that they can be stored and transmitted efficiently. Because of these reasons, we are using the transforms for processing of digital images. That is transforms introduction in digital image processing. So with this, I'm actually wind up this particular session. And what are the different transforms we have? And what is the basic advantage of the transforms? And what are the properties of a two-dimensional DFTs or FFTs that we'll see in the next session. So image transforms and the classifications. Based on these classifications, what are the different transforms we have? And what are the properties of these transforms? That as a continuation, we'll see in the next video.